That's good. Okay, so now we have Spencer who will tell us about Ahlfors currents and symplectic non-hyperbolicity.
Okay, thank you for inviting me to come speak here. Very happy. Um, Let me first give some classical motivation for this talk. And it's like many things, it starts with Gromov in 1985. And the theorem is for any J tamed by the standard Fubini-Schudy form on CP2, there's a rational curve. And you prove this using Gromov compactness. You get a nice family of curves. And using a similar argument, using sweep-outs of curves and so on, you can use this to prove the symplectic structure on CP2 is unique. So this is a theorem of pure symplectic topology. It doesn't mention pseudo-holomorphic curves at all. And this technique extends by work of McDuff and others to rational and ruled symplectic manifolds surfaces. In general, for manifolds where you have lots of rational curves, you can use them to get these topological classification results, which are just amazing. And if you try to extend these to the next simplest case, the 4 torus, they fail completely because it's symplectically aspherical. It doesn't have any rational curves to work with. And even if you just look at a general complex torus, it doesn't have typically any closed curves. So the techniques fail completely. Nevertheless, if you look at, say, a complex torus, it always has holomorphic curves parameterized by C. And this motivates this proposal by Gromov in 2000 that perhaps you can use these complex lines, so not rational curves, but lines, to prove some kind of uniqueness result for symplectic structures on the 4 torus. In this line, there's this fantastic theorem by Bangert that says if you have a symplectic torus, it always contains, for any tamed J, complex line. So this is amazing, because if you think, how would you prove this, right? The way you prove this result by Gromov is use Gromov compactness continuity argument. Well, what can you do here? It's not, C isn't compact. How are you going to deform it? It's a complicated issue. It's a very short paper. It's 10 pages, but it's also very ad hoc. So it shows that there is something, but it doesn't indicate how to study it in general. So this, the existence of a holomorphic line in complex geometry is called non-hyperbolicity. And this indicates that there's something symplectic about it. There's some possibility of symplectic non-hyperbolicity. And really, if you're going to carry out this proposal, you need a very topological symplectic understanding. It wouldn't do to have to carry around all these analytic estimates that you might have to use to deform C. So in complex geometry, they have a way of, instead of working with C, you work with disks. They call it the Brook principle. And in this case, instead of studying complex lines, you might study Ahlfors currents. So these are currents which are the limits of sequences of disks whose boundaries become negligible. So it might seem like a maybe strange definition. Here are 2 examples. The currents of integration over rational curves and tori are both Ahlfors currents. So for spheres, you can just take larger and larger disks in the sphere. And then for tori, you take large disks in the universal cover. And both of these examples are closed. They have homology classes. And this is actually typical for Ahlfors currents. you see this estimate that the length of the boundary goes to 0 means that the limiting object, the Ahlfors current, has no boundary. So it defines a homology class. So you can integrate forms against it. You can take intersection pairings. It has a full life as a topological object. So it's really a much, much easier to study than a complex line directly. And as far as generalizing Bangert's theorem, we have this theorem. It's actually two separate theorems. It says in a compact, almost complex manifold, the existence of an Ahlfors current and the existence of a complex line are equivalent. So the existence of an Ahlfors current is due to Ahlfors. It's called the Ahlfors lemma. That's why they're called Ahlfors currents. The converse direction is due to Duval. And he actually proved a stronger theorem. He showed you can get some geometric control on the curve you construct. But there's not a one-to-one correspondence. And if you just unravel the definition of Ahlfors current, this says that the existence of a complex line is equivalent to the existence of disks which satisfy arbitrarily strong reverse isoperimetric inequalities. So inequalities of this form. So you think as k gets larger and larger, you still need to find disks for arbitrary k. So, okay, at some point you're working with analytic things, you need some estimate. But this is a very pleasant estimate. It's geometrically interpretable. It's invariant under reparameterization. It's just a geometric inequality. And the motivation for this talk, the thrust, the point I'll try to defend, is that Ahlfors currents are like rational curves. And you think, okay, they're like lines which are like rational curves. So it's kind of a nothing analogy. But it's a shockingly strong analogy. So first, let me say, as far as construction goes, rational curves are frequently constructed using a continuity method. Like I said before, you deform them and then you use Gromov compactness to show that you get a limit. Complex lines, it's very difficult to do so, but the following theorem is proved using a continuity method. So if you have a closed symplectic manifold that retracts onto a Lagrangian, just want to point out here, it's a retraction and not a deformation retraction. So for instance, every Riemann surface retracts onto a Lagrangian. It's a very flexible condition. A deformation retraction onto a Lagrangian would be impossible. So you assume X retracts onto a Lagrangian, and it admits a metric of non-positive curvature. Then, when you multiply it by a torus and deform J, the torus deforms as an Ahlfors current. So for any J, there exists an Ahlfors current, and therefore a complex line. And I just want to point out this assumption 2, I just stated that way for simplicity and because it's more intuitive, but it can actually be replaced by a purely topological assumption, or symplectic topological. So you can assume instead that omega is symplectically aspherical, and that the fundamental group of X has at most quadratic homological Dane function, so some geometric group theory. This is kind of an abstract theorem. Let me give an example. If you take a product of Riemann surfaces with a product symplectic form, if any J contains a complex line, then every J contains a complex line. So they're like indestructible. And this, if you take all of the Riemann surfaces to be tori, this is Bangert's result. And in general, this answers a question posed by Ivashkovich and Rose. It's not maybe especially clear how this result implies this result. So let me just explain. It's a proof by cases. So you have three essential cases. The first on the top line is where some curve is rational. Then it follows from Gromov's work in 1985 already that every J contains a rational curve, and therefore in particular a complex line. So in the next case, depicted on the second line, is where you have no rational curves, but at least some curve has genus 1. And then because there are no rational curves, the total manifold has non-positive curvature. And because every Riemann surface retracts onto a Lagrangian, so does the product. So this satisfies the assumptions of this theorem, and in particular, every J contains a complex line. The remaining case is when every surface has genus at least 2. And in this case, it follows from Gromov's work on Kähler hyperbolicity, really the notion of Kähler hyperbolicity from 1991, that no tame J contains a complex line. So that's the dichotomy. In the first two cases, you always do, and in the last case, you never do. And that's how this corollary is proved. But beyond the theorem and the corollary, these are maybe proofs of concept. The exciting point is the construction. By working with Ahlfors currents, you reduce this deformation to just working with disks. And the existence of disks with Lagrangian boundary conditions is one of the standard methods. People say this all the time. The additional ingredient you need to get an Ahlfors current are these reverse isoperimetric inequalities, like I mentioned. And for reverse isoperimetric inequalities with disks with Lagrangian boundary, this has been studied by Groman and Solomon in 2014 and Julian Duval in 2016. The novel point is they don't so much care about what the constant is, but that's the key point for me. I provide a lower bound for the constant in the reverse isoperimetric inequality, which depends only on the C0 bounds of J. So the idea is if you have, say you're just in Rn, if you have some torus, you want to scale it and hope that the constant goes up. But when you scale it, J also scales. So it's C1 norm and everything blow up, but it remains uniformly bounded. So by working with the C0 bounds on J, you can use scaling arguments and enter the large scale geometry of the universal cover, which is broadly controlled by the fundamental group, just as a point of geometric group theory. Okay, so Ahlfors currents can be constructed with continuity method. Another point in the analogy is that bubbling. So bubbling of rational curves is the kind of key source of flexibility for J holomorphic curves in general. So if you have an area bound and you fix complex structure, any lack of compactness comes from bubbling. There's a similar result for complex lines due to Demailly in complex geometry. So he says if you have a sequence of curves whose areas grow faster than their genera, then there exists a non-constant J holomorphic map from C, complex line. The idea broadly is that the genus of a surface, of a hyperbolic surface, is its hyperbolic area. So if the area blows up with respect to the genus, that means that the map has some area derivative blowing up. And if you rescale near some point, you should be able to extract this complex line. Maybe the problem is you don't know anything about this complex line. And it's very difficult to totally prevent the existence of a complex line. So my second result is that instead of just extracting some complex line, you can show that a subsequence itself converges to an Ahlfors current. So in the analogy with bubbling, maybe Demai's result was if bubbling doesn't occur, you have compact moduli spaces of curves. And then this is more refined analysis where you can prevent very bad cases of bubbling from affecting things. So for instance, because Ahlfors currents have homology classes, they can be controlled with cohomology and forms and so on. In particular, you can use homological criteria to show that for some sequence of J-homomorphic curves, their genera bound their areas. So this is the reverse of the Castelnuovo bound, which people study with respect to this Gopa-Kumar-Vafa conjecture. So you're able to get bounds even in the presence of complex lines just by adding homological assumptions. So it's like a relative form of Demai's result. And just to maybe highlight a little bit of the difference, I have this graphic. So if you imagine you have a genus 2 surface and there are just two bubbles blowing up on it, Demai's result is a local procedure and it will pick up one or the other, but it can't pick up both. This result picks up both. So it's a global kind of rescaling. And it actually, it's kind of very quickly proved, just the front and back of a piece of paper, using the equidistribution of spheres in hyperbolic geometry, just a pure geometric result. The last point of this analogy between rational curves and Ahlfors currents that I'll talk about today are their moduli spaces. So the moduli spaces of rational curves contain lots of information. So much information that lots of people say that's like kind of the only thing people study in symplectic geometry, which I think is, well, it presented a difficulty for me when I was talking about this early on in the work, because I would say, oh, I'm studying Ahlfors currents. People say, oh, but what about their moduli spaces? And the difficulty is that moduli spaces of pseudo-homomorphic curves, because they're solutions to an elliptic PDE, are finite dimensional, they're kind of like manifolds, whereas Ahlfors currents naturally lie in a linear space. So there's no hope for that kind of thing. It's not even right conceptually. But you can ask, what linear structure does their moduli space have? It turns out it has as nice a linear structure as you can expect. The space of Ahlfors currents in a closed connected almost complex manifold is a compact convex set. So the compactness was already known, it just comes from Banach-Aloglu, but the convexity is new. So in particular, because the image of a convex set is convex, the space of homology classes represented by Ahlfors currents is a compact convex set. And the space of Ahlfors currents representing a given homology class is a compact convex set. So there's some hope that you can use convex geometry to get information about your symplectic manifold. The same way they study the cone of curves in birational geometry or things like this. And there's this somewhat evocative example. If you take a rational curve bundle over a Kähler manifold, then the space of extreme points, which is some convex geometric notion of Ahlfors currents in the fiber class, is exactly the moduli space of rational curves. So it seems like these convex spaces do contain quite a bit of information. Yes, so to summarize, these complex lines, this notion of complex hyperbolicity, it's clearly something new. Bangert's result is not derivable from just the closed pseudomorphic curve theory because that degenerates for the torus. So there's something new, and I think with Ahlfors currents, it can be understood and incorporated better into symplectic topology, and it invites the use of new techniques. So Bangert was not a symplectic geometer. He's known for his work on geodesics, and his proof uses geometric measure theory. And the proofs of these theorems use kind of a variety of techniques, and it seems like a very interesting problem. Thank you for your time. Thank you.
Thank you. Any questions?
Could you please explain connection to den function?
Oh, yes. So it's kind of related to this last point below. So this work by Duval shows that this reverse isoperimetric inequality comes from a monotonicity formula relative to the Lagrangian, which comes from the holomorphic curves being like quasi-minimizing. So in order to use this, especially at large scales, you need to be able to construct comparison surfaces to get non-trivial inequalities. So you use the Dane function to say, at large scales in the universal cover of your manifold, you can construct pretty efficient comparison surfaces. And that tells you that the areas of pseudomorphic curves have to be pretty small, and then they act like minimal surfaces, and you get this monotonicity formula.
But do you still need some Lagrangian or?
Yes, you still need a Lagrangian.
Because you kind of emphasize that you have this topological condition, which is not symplectic. So do you mean that, could you please show this slide? Yeah. So you said, so instead of metric of non-positive curvature, you need this, but you still need this Lagrangian.
The first assumption you still need to.
I see. Okay. Thank you very much.
The second assumption, part of it is that it has to be symplectically aspherical, which is again like a symplectic assumption. So they're like symplectic topological.
Okay. Thank you.
Yeah.
Maybe clarification is necessary for me. So when you say that X retracts onto a Lagrangian, what exactly do you mean? Isn't there a kind of volume issue?
No, I think this is exactly the difference between retracting and deformation retracting. So if you look at like a torus as a product of circles, the projection onto one of the coordinate circles is a retraction because it fixes that coordinate circle.
Okay, thanks a lot.
Okay, so thank you, Spencer, again.